So in this video, I want to answer the question of why z-scores. Why do we use z-scores? Why can't we look at how the normal distribution is broken up and then just take proportions of those segments and add them together? It's a misconception that I had in the past, and I want to correct that so that other people don't make the same mistake. So if we look at this question, it says on this intelligence scale the average IQ is 100, standard deviation is 15, so I have a mu of 100 with a sigma or standard deviation of 15, and I've written it out here with my normal distribution where I have my mean of 100. I've applied the standard deviation to give me 115, one standard deviation, 130, 145 for standard deviations above the mean, and so forth. And let's answer this first question. Well, what is the percentage of the population that has an IQ that's less than 85? So we go over here and we see, well, 85 is exactly one standard deviation below the mean. And the population that is going to be below that consists of these numbers here. So I'm looking here and I'm saying, well, what percent of the population is going to be represented in the area under this curve? Well, that's these numbers here. It's going to be the 13.5% plus the, so we could write it here, the 13.5% that is represented between 1 and 2 standard deviations, the 2.35% that's going to be represented between 2 and 3, and the 0.15% that's going to be represented beyond 3, which is a total of 16%. Which is great, and it's easy to answer. But then we have a question like this. Well, what percentage of the population has an IQ that is less than 107.5? Well, 107.5, well, that lies right here, and it's not an exact standard deviation. So now I want to answer this question here. I want to say, well, I know that everything to the left of the mu, it represents 50% of the data. I also know that between the mu and one standard deviation, well, that's 34% of the data. And I know that from my empirical rule that says between one standard deviation below and one standard deviation above is 68% of the data. So half of that would be 34. And I noticed that 107.5 is exactly halfway in between 100 and 115. So, well, can't I just say, I know that this is 50% of the data, and then can't I just take this 34 and cut it in half and say, well, the 50% plus half of the 34, or 67%. And why can I not do that? Well, the answer is I need to use a z-score, and the reason why is because we're talking about area under the curve. So let's look at this little cutout here. Between the mu and one standard deviation here, I see my halfway mark. Well, let's compare the area at the halfway. If I look here and I split this in half, notice I have very different areas here. If I look at this portion from the mean to 107.5 obviously has a bigger area than this portion from 107 to one standard deviation. And it's because it's curving. So I can't just take it, say, hey, this is halfway in between, take half of 34, because it's not exactly proportional. There's more of the data in this orange area than there is in the green. So that's why we have to use our z-score table. And we say, well, okay, well, what's 107 is our data. the mu is 100, sigma is 15. Plug it in, data minus the mean divided by the standard deviation, I get 0.5. And come and find that 0.5, that's going to be at the intersection of 0.5 and 0.00, which is 0.6915. So as I turn that into a percentage, it is 69.15%. And as you see, as compared to what we thought it would be, 69.15% is a little bit more than that, which makes sense because there's a little bit more area in between the mean and 107.5, as opposed to, as the curve gets smaller here, having less area here in the green. So my final answer to this question, this question here is 69.15% lies below. From this portion, from here, all the that is represented here under the curve is 69.15%.